Hello again, folks. Today we're going to be starting completely fresh. Right? So if you want to, maybe in your notes kind of fold over a little triangle like that so that you can separate out test number 1 material, and that will be building towards test number 2. Right? And basically, it's 2 chapters. It will be, not today, but I mean like in general. Chapter 7 is the metric system. And then immediately after that is geometry. According to the calendar, as you can see, what's planned for today? Right? Wednesday the 14th, we're going to do section 7.1, 7.2, and 7.3. Right? And then we're done for the week, and I'll see you again on Monday. Jumping the gun a little bit, right? Get out of here! Alright, but no, I'm happy to have you. Let me get busy. The packet that I have for you today, this is the top sheet. This is the most important thing. I'm going to build a summary with you so that when you do your work, all right, you have a reference. All right. I figure that, and this is a good sort of idea if you're teaching kids. All right. Make a worksheet for them and then sort of walk them through the process. Right. It's not really like they have to do strenuous sort of mental activity. They're trying to build a reference, right? And if they handwrite something, I'm more inclined to remember it. Anyhow, this is the sheet behind it. I kind of gave you this a while ago, but I'm going to revisit it because I think it's practical. This is the kind of thing, this model, if you will, that's useful if you're in a chemistry class, really, where you have to do unit conversion. But since we're going to be doing unit conversion even in the metric system, this idea, which I'll get back into, all right, is kind of useful. So I'm going to have this available in the chapter 7 page, all right, in Canvas so that you can print it. And then there's one kind of nice reference that I stole from the textbook. It's a little blurry, which is temperature scales, right? What is the equivalent of Celsius and Fahrenheit? So part of the barrier, fortunately, to the United States joining the rest of the planet is the affinity that we have for the systems that we already use. Right? If you grow up with, say, something like the Fahrenheit temperature scale, right? You, believe it or not, you associate a feeling with a number, right? So, like, for example, if somebody told you no unit, they just simply said, it's 20 degrees outside, right? An American would be like, ooh, brr, Why? Because we think of 20 degrees as being a low number, all right? That means cold, means brr, but 20 degrees in Celsius is room temperature, right? It's the equivalent of 70 degrees on the Fahrenheit scale, which we're used to. So, that's a part of the burden of being a teacher, all right? Getting people to sort of wean off a feeling, right? To break with a feeling, all right? That they have maybe even subconsciously attached to something, all right? Anyhow, let's get into this stuff. All right. Just to give you an overview, as always. And let's see if I need the light. I don't think so. Okay. It's a little afternoon right now. So like the light is almost ideal. We are going to discuss systems of measurement. All right. And just to get your feet wet here. There is, in the United States, all right, 2 systems, really, all right? There's what is the imperial system, because we were once a colony, all right, but we have since taken to calling the customary system almost defiantly, all right? That's basically what we take for granted, all right? If you have something like, for example, miles. Right. That's a holdover from the imperial system. Right. Basically, miles is is, it's from the Romans actually. We adopted the unit of miles from the British Empire. That's the imperial part of this, all right, because we were once a colony. And the British Empire were once, basically, England, all right, was a colony of the Romans. So this is actually, some of the units, probably not all of them, but some of them are in fact ancient, all right, which doesn't make them bad, all right. It's just that they were not made necessarily with foresight of scientific endeavor, all right. Anyhow, miles is just an example. It comes from the Romans, right? May not have been exactly the same, but the idea of having this unit, right, that measures vast distances, all right, this at least goes back as that far in time, right? So it's like 2,000 years ago, all right. Then there is the system that basically the rest of the world uses that we need to, all right, and that is the metric system. Right. Also, it's originates from roughly 1790, right, during the French Revolution, which is why, although we refer to it as the metric system, right, it's the standard international system of units, the French equivalent of that, right, the Système International des Units. If I'm pronouncing it correctly, and I'm probably not. I wish I were. Anyhow, this is something that was designed from the onset, right, to be very strategic and easy to use, right, which is why it has applications in science and engineering, right, and interestingly, right, it's in world market goods. Right? The first thing that comes to my mind when I say that, world market goods, is Coca-Cola. Right? At some point in the 70s in the United States, right, there was the talk that, oh, we're going to convert to the metric system, and there was, that initiative, but it never really quite reached fruition. We sort of started it, right? Companies like Coca-Cola, which produce Coca-Cola for the entire planet, basically. If you go to India, there's Coca-Cola likely. If you go to China, I would bet there's probably Coca-Cola there, all right? Even in Soviet Russia, they had their own form of Coca-Cola, all right? Anyhow, South America certainly has Coca-Cola. So it would be in the best interest of the company, right, to bottle their substance, right, in a unit that people, are familiar with, right? And since most of the rest of the planet is now metric, all right, they don't have to have two different systems, unless technically they still manufacture in the United States, all right? Anyhow, interestingly, right, when you go to the supermarket, what do you buy a soda in oftentimes? Liters, right? No other substance, right? When you get milk, it's in gallons, right? When you get orange juice, it's in a half gallon or thereabouts. It's a little bit shy of that, actually. 64 fluid ounces would be a half gallon, right? And it tastes like 59 because they're being cheap, all right? Anyhow, soda got on board on the metric system a long time ago. Anyhow, this is the topic for today, the metric system, right? And again, it is the better system because the unit conversions are easier. It was an idea. Anything that is, I'm not saying that we should do away with anything that is traditional. I mean, that's just paying respect to the ancestors, and that's not a bad thing. All right. But for the sake of a global, sort of mindset, we recognize we're part of a planet, not just a country or a neighborhood or a state, All right. Having something that unites us like that, a common system of units, namely math, right? Is a good thing, In terms of language, it was a long time ago a language contrived called Esperanto, which basically had the same idea, all right, only applied to speaking, rather than something that was language, rather than mathematics. a second overview here. We have basically to discuss different metric units for different purposes. All right. So there's the three, well, in this case there's four, all right. But there's two that are very, very closely related. All right. So the metric units that we have to discuss are basically metric units for length and capacity, right, and then mass is a technicality, and temperature. Right, temperature is very intuitive, we know what that is, right? Capacity might be, just because of the phrasing here, might be a little bit more vague. Basically, capacity is a volume. All right? And there's a unit for volume that you could either, which is famously liters. Right? I mentioned this before. I'm spelling it perhaps corrupted, the American way, which is L-I-T-E-R rather than R-E. Okay? Thank you, Noah Webster. Right? Anyhow, length, right, is measured in meters, right, which is about, it's a bit larger than a yard, right, if we Americans are familiar with the yard as being 3 feet, right, and that's 36 inches, and I want to say a meter is like 39 and change, you know, it's a little bit larger, so that it's about as wide as this board almost. Anyhow, length is something that's one-dimensional. Right? And in theory, you could calculate an area from lengths. Right? But just bear in mind, an area is two-dimensional. And if then you calculate using a third dimension, you can get to volume. Right? Okay? So there's kind of a roundabout way to calculate a volume rather than using the unit that is a liter. Right? You could use either liters, or in theory you could use cubic meters. All right? Mass is not weight, right? But it's used almost synonymously with weight. All right? The unit for this is the kilogram. All right? Just think of basically measuring a person's mass would be appropriate in kilograms in the same way that measuring a person's weight would be appropriate for pounds. Right? A pounds is also a Roman unit. Right? It's way old. Right? And then there's temperature, right, which is in degrees Celsius. All right, as opposed to degrees Fahrenheit, so you would see something like that. All right. These are different physical quantities. Now, what I want to do is basically assemble this, or work through this with you. It's, at least initially, it might seem an unnecessary, more complicated way of doing things. I put these number lines here as the more efficient way of converting units, right? But I want to build this reference with you first, right? You're not going to need the whole thing. It's really this range here. Just so that you have to have a reference for the suffixes, pardon me, the root words and the prefixes, right? Because they describe basically the size of the unit. So let me erase this again. You could use this for all 3 sections and beyond, really. If you take a science class of some sort, you could use it there. That's an interesting thought. I don't want to really mess with anything here too much. I could sort of orient my board differently. I wonder if I should do that. Maybe I will. I just don't want this thing to fall on me because it will. Well, tell you what. Let me see if I can get away with doing this. Okay. And then maybe I could scoop this around. This is the second piece of acrylic, which is cracked, unfortunately. You break very easily. All right. I have to sort of draw the diagram as I don't have a projector, so humor me for just a moment. All right. Where I have designed the worksheet is that it looks like this. There is a very obvious longer set of bars here in the center. All right. And this is where I'm going to have to write base units. Okay. And then above that, you'll notice that there are slightly shorter lines, like this. All right. 3 spaces above and 3 below. Okay. And we'll start with that. All right. Now, the base units, as I alluded to before, all right, are the meter, right, which is abbreviated by a lowercase m. Right? The liter, which historically, and maybe I gotta get with the times, but I'll show you anyway. The liter, spelled the American way, which is ER as opposed to RE. Used to be capital L, and I want to say if you were taking a chemistry class, it would still be that way. One thing I noticed interestingly is that in our textbook, they opted for a script L, which is certainly nothing wrong with that. It's stylistically more pleasant, perhaps, and it would be consistent too, as this is lowercase, right? But that's what I think most chemistry books would have, so just beware, all right? And then there's the gram. And hopefully this is legible, so, which is a lowercase g. I'm just going to extend this ever so slightly to encapsulate. All right. So base units, measurements of length, measurements of capacity, which is really a volume, measurements of mass, all right, and the Celsius scale is its own thing. All right, you could have, you know, we use just Celsius, you don't have like micro Celsius or anything like that. Anyhow. Notice these abbreviations, M, L, and G, even if it's a script L. All right. To these, all right, I'm going to put little hyphens like this. To each of these, all right, prefixes can be attached. All right. That's what I want to put in these 3 spaces here and in these 3 spaces here, just for the reference. All right. Just above, all right, this base units line, all right, what you would have is, which is a different color, let's see, I'm going to go with red just because it's easier, all right, there is the prefix deca, all right, which is abbreviated DA, right, hey DA, all right, and I'm going to put the hyphen this way, meaning that you could have a decameter. Right, you could have a decaliter, you could have a decagram in theory. Some of these are less common than others, but it is mathematically possible. All right, just above that, all right, there is hecto, which is abbreviated H. Right, and also would be attached to any one of these: hectometer, hectoliter, hectogram. All right, and then there's the more common kilo. Which every time I say it makes me feel like I'm some kind of like drug lord, you know, like, how many kilos is it? You know, bad waka waka. Whenever you watch movies or something, right, it's always like, hey, I got 5 kilos or whatever, you know, meth dust, you know, chalk, you know. I'm gonna stop now. Anyhow, so kilo, all right, attached to meter, liter, or gram. Okay, then there is the opposite side, okay? If you're descending here, all right, you have something that is unfortunately similar to deca, which is deci, all right? And that's just lowercase d, all right? And then one down from from that is centi, which we all familiar with, C, all right, and milli, which is, it shares the same abbreviation as the base unit, which is unfortunate. I have noticed that in math in general, the letter N gets used a lot, all right, for better or for worse. All right. Let me just grab something upstairs. I'll be right back, because I want to point at it. I had to go through an old box. Right? Here's a ruler, all right? Just the kind of ruler that you would get in a 99-cent store or what have you, a dollar store. In fact, it even says what it is in the back. Wood ruler. Anyhow, every ruler that I've ever seen in my entire life, all right, has inches, because that's the customary system for us, right? And then on the other side is centimeters. So when it comes to length, at least, Americans have a natural relationship with at least centimeters and millimeters. All right? A decimeter technically is hidden in here, because a decimeter would be exactly 10 centimeters, right? So it would be this distance from my thumb to my pointer here, right? And you could fit, in theory, 3 decimeters on here. Anyhow, it's nice to have some kind of established relationship with the system, right? We really do, we just don't take advantage of it enough. You'll notice that there are spaces, right, a little bit below this here. And I'm gonna mention them. They're not too practical because they don't come up in ordinary life too often, but do this. Make a dot here. Put this in blue, just because those spaces don't have a unit name, right? And then on the third one here, put micro. Micro is abbreviated by a Greek character called mu, which kind of looks like a very stylized fancy U, right? Like this. It's not an M really, but I want to say it's pronounced mu, M-U. Right? Anyhow, that would be yet another one of these prefixes. In fact, if you go down a little bit further, another 2, you would get to something called pico, which is even smaller. It's abbreviated P, right? And then femto, alto, zepto, and yocto, which sounds like Marx Brothers, if you ask me. Okay. The unfunny Marx Brothers. Okay. Like Carl. Yeah, he was not funny. Okay. Now that's a little bit out of the frame, right? You're probably not responsible for these micro, beyond milli, because what is in red here, this range of units and their prefixes, right, are pretty much the standard model, right, that is applicable to real life, right? If you go into a science, micro, and then down further still pico and so forth, might be applicable to, you know, microbiology, right, or you know, even physics, right? Anyhow, on the flip side, again, I made kind of some spaces here. Actually, you know what? I'm jumping the gun here. Let me make one correction. Pico, I'm not going to be able to fit it, is the problem. Three spaces under micro is nano, correction, which is N. Okay. If you go up 3 spaces from kilo, you get to mega. I'll put that here. Mega, sounds like Sega. Capital M is what they use. Again, M gets thrown around a lot. If you go up an additional 3 spaces, all right, just like down from micro is really nano. Try just dark and didn't consistently make in blue. Should have nano. Okay. The next one above that would be giga. Right, if you've ever seen Back to the Future, you've probably heard this unit before. 1.21 gigawatts is what you would pronounce it as. Not gigawatt, but that, you know what? Giga, tomato, and the same difference. Right, anyhow, it's a watt, a very large watt. And then above that, further still, which again, you're probably not responsible for, would be another 2, 3 up would be tera, all right? Which is abbreviated as a T, all right? So just to show you really quickly, is kilo, 3 spaces, this third one is mega, 3 spaces is giga, all right? Another 3 spaces, the third one is tera, all right? On that side, all the way at the tippy top. And then there's other ones, there's peta, exa, zeta, and iota, all right? They're getting into astronomical size things though, so you know, like not too common are you seeing those. All right. Now, just basically showing you this because I want you to be familiar with this range again. All right. Now, how do you convert from units from one to another? It depends on where you start and where you're going. So. There are these blue arrows you see that look like this. And I drew them like so. If you're basically going down, right, downtown, all right, then what you need to do is move the decimal point wherever it starts towards the right, which is that way naturally. If you're going up, right, wherever it is in this list, up, and away, all right, then you need to move your decimal point to the left. To the left. Okay. So, down, right, up, left. Right? This may sound silly, especially compared to the more simple way that you'll see in a moment, but I've found this is good because it gives a person a feel for what is large versus what is small. All right? One needs to get used to thinking about it this way. All right? Now let me push this kind of aside, hopefully it won't fall off the thing here. All right? And I'll do a couple of examples with you. All right? Just to kind of get used to it. Please don't fall. Okay. Not cooperating. Nope. Alright. You know what I'm going to do? I'll make it sit on my eraser. There you go. Take that. Alright. It's crooked, but you get the idea. Alright. So here's an example. If you had to convert, right? The most basic way, 457.3 meters, and we're just sticking with the metric system itself, right, to so many kilometers. Let's go to the point in the picture, right, where meters resides. This is again going to annoy me because it's not right. But let's see. That's a little bit straighter. meters is here to start with, right smack in the middle. All right. If you're going from this lower point up to kilometers, which is where kilo is, right? You're going up this list. So you're going to have to, you'd be obligated to move your decimal to the point left. Now the question is, how many spaces? Think of it like Candyland, you know, like you start on a space and then you count 1, 2, 3. All right. So if you're here and you're going there, it's up 3. 1, 2, 3. So therefore it is left 3. I'll move this aside now. Okay. All right. So if this is your number, 457.3, there's the decimal point. Sometimes the decimal point is not obvious. Like if you add a whole number, it may be obscured. I would purposely write it. Anyhow, we're going 3 spaces left. So make 3 waves. 1, 2, 3. And then just to distinguish it from where it was to where it's going, I'm going to exaggerate this. All right. What does that mean? It means that 0.4573 kilometers is what 457.3 meters is. These are the same, all right? They're just expressed in different units. That usually gives people a little uneasiness the very first time. They're like, that's a smaller number. It's a larger unit, all right? You have to convince yourself that is a much larger unit. That's why the decimal is different, all right? This process of moving is really because these are based on powers of 10, right? All right. And when you convert from a smaller unit to a larger unit, you're basically dividing by 10, right? Dividing by some power of 10, right? The effect of that is that it just cuts the decimal place over. If you were going from a larger unit to a smaller unit, right, then you would be multiplying by some power of 10, which is why it ends up, you know, somewhat suspiciously, maybe is not the right word, but makes you doubtful, right, that it's the same thing because you get such a large figure. All right. Anyhow, stylistically, there's something that you can do extra. 0.4573 is correct, all right? But often is the case, what you will see is a little 0 tucked in the front, right? In other words, put here, 0.4573, all right? That is just meant to make it a little bit easier to make the decimal point obvious, supposedly. All right. It's supposed to, it's more of a formality. It's not that you really have to do that, but I would anyway, because it's considered good etiquette, if you will. All right. As a matter of fact, and I don't want to digress too much, but around the world, right, the way that we use commas is the way that they use periods. So for example, and vice versa, right, in the US, right, versus the world, should never be the case. Right? You might see a number like 3.5, right? Whereas elsewhere around the world, you might say 3,5, right? It's understood that these are doing the same job, even though they're not the same symbol we would normally use, right? All right. And it's exactly the opposite with very large things, right? So for example, if you had in the United States, 3,644,700,000. Right. Elsewhere around the world, what you will see, instead of having commas, is that they will put periods like this. Right. And it means the same thing. Right. The comma here is the period there is the comma here. They're interchangeable. We group things in sets of 3, right? What the book suggests we do, and I like this, right, is that leave an obvious space, right? That's kind of how you could tell that you have a nice textbook. I know it's a very subtle thing, but a textbook that is well written, a math textbook, all right? When they're writing very, very tiny things like, let's just say you had 0.0007, all right? What they would do is that they would leave an obvious gap all right, between every set of 3. It makes it a little bit easier to read it, all right? If you've ever had a test where you have multiple choice and you see a bunch of zeros, it can be kind of blinding, right? Especially if there's a lot of them, you know? Imagine you had that, right? You'd be like, how many zeros are there? Would make me dizzy anyhow. And I'm pretty dizzy to begin with. All right. Anyhow, instead of using commas, all right, we could use a gap, basically, right, in groups of 3. Let me erase this. I'll do a couple more of these, and we'll shift gears. That looks like a happy medium. Okay, good. All right. Here's another one. All right. Suppose that you had to convert 14 grams. And it does take some getting used to if you've never used the metric system, what the abbreviations stand for, but G is just grams. How many CG is that? CG would be what? Centigrams, so it's really down here is where we're going. If you start on a base unit and you're going to CG, you're going down. So if you're going down the list, you're really multiplying by some power of 10, right? And then without having to complicate it, just go from here 2 spaces. So if it's starting here, you're going here, 1, 2. That means you move the decimal that really should be there to start with, but it isn't, right? And then you would make 2 waves. So you're gonna go 1, 2, and then I'm gonna just exaggerate that. And then in the gap, you fill in these phantom zeros here. So 1400 centigrams is 14 grams, right? I know that a person superficially will go, oh, geez, those can't be the same thing. How could 14 be equal to 1400, right? They're equal because they're expressing the same physical amount of something using 2 different units. This is using sort of a mid-sized unit, grams, and this is using a puny unit, right? So it would take more puny, tiny little units to express the same quantity. All right. Now, I'll do, let's see. Do one more with this chart, and then I'll show you what the arrows are all about, the sort of number lines that I have written here. Okay. If you were to convert 80 kilometers into so many centimeters, that's not the worst of the worst in terms of conversions, not the most drastic, I should say. All right, but it will be, expect a large number here. All right, how come? Because you're going from the very tippy top here down to something nearly at the bottom, right? And when you go down, you're multiplying by some power of 10 without consciously thinking about it. You're just observing the effect. The effect is to move the decimal point towards the right that many spaces. So if you start here and you're going here, count from here. 1, 2, 3, 4, 5. You're gonna make 5 waves. Start with 80, put the decimal point where it ought to be, right? And then proceed to make 5 waves. So you'll go 1, 2, 3, 4, 5, right? And I'm gonna just exaggerate that one. And then fill in the voids here with some zeros. All right. Now, if I write this in the traditional way, in the United States, all right, it would be this, 8 million centimeters, right? If you were to do it elsewhere, it might look like this. At least that's what the textbook indicates. All right, and just to sort of have a happy compromise here, which I think is better anyway, all right? Make obvious gaps. So you put 8 and then group of 3 zeros, and then a second group of 3 zeros, all right? And then the unit. centimeters. That's the best way, really, right? Not to corrupt your opinion. Yeah. All right, 8 million centimeters is 80 kilometers. All right, again, a person would go like, what do you mean 80 is 8 million? How can that possibly be? Because this is a very large unit, so it takes less of them to express the same physical distance, right? Whereas this is a tiny little unit, and you know that, all right? Here's a ruler, all right? Centimeters, right? I'm on the wrong side here, all right? 1 centimeter, all right, is just this distance from here to here. So it's going to take quite a lot of them, apparently 8 million of them, right, in order to express the same physical distance. Okay. Now, let me get rid of this board here. All right. And you certainly please have it as a reference, but I'll show you what is probably a little bit more intuitive now that the names and the prefixes are all discussed. Right? It's often good to have an alternative way of looking at something, just in case one way is confusing. So I drew on this paper a bunch of lines, right, what look like this, off to the side. I drew a blue line with some increments here, and I drew a green line with the same increments, and a black line, I believe, right? What you could do, again, if you're not really comfortable with the metric system yet, right? And perhaps you are from, maybe originate from a place where, it's normal, right? And I wish it were normal here, right? You may not even need to do this, but human may, right? In the evidently larger increment here, the middle, each of these, I just want to put the abbreviations for the base units and their prefixes around it. So, meter, right? And here I'll go with the liter for right now. And I should probably not use red in the case of green. I will use blue, right? And then gram, okay? A unit for measurement of length, right, of capacity and of mass, right? And then I'll, to the right of it, put the abbreviations that would be attached to any one of these. So if it's, next one down would be decimeter, dm, and then centimeter, and then millimeter, right? And then on the flip side here would be dam, right, and then hm, and then km for kilometer, okay? Similarly, you could have a deciliter, right, a centiliter, or more famously a milliliter. Right? And then there's a dal. How often does that get used? Hectoliter, kiloliter. And dg, decigram, centigram, and milligram, which I have a fondness for because I always think of a vitamin whenever I see that, right? Right. And again, the metric system is very much disguised, in ordinary American life, right? It shouldn't be, but it is, right? And it's getting in through the vitamins, everybody. Your Flintstone is in milligrams, right? DAG, DAG, HG, kilograms. Right. Anyhow, you could go through the same process, and this is why I say it's a little bit more intuitive. Because the leaps that you would make along the graph, right or left, are the direction of, instead of figuring out how to translate down means right and, up means left. So here's a couple of those. Let's say that you had to order from smallest unit to largest. Length. These figures. All right, we start with 3.4 M. All right. The next is 3,421 millimeters mm. M&Ms. All right, and 104 centimeters. Okay. All right. Now, as will always be the case, all right, comparisons can only be made when there is a consistency in the unit. So what you have to decide for yourself is, decide which unit to convert all to. It doesn't matter as long as you either get them all to be meters, or you get them all to be millimeters, you get them all to be centimeters, then there's no problem. Right? I think I went with milli, all right, just because it's the smallest unit. Right? So these other things are going to be larger than what they are. Right? This will be converted to millimeters, and this will be converted to millimeters. Right? Now, if I incorporate, and I'll do this one first here, 34 meters. If I incorporate the graph here, the number line, right? Again, if the unit is M, you start here, right? And then go to what you're converting it to, milli. So, come on, Matt, go. All right, millimeters is here. So you're gonna go 1, 2, 3 steps, 3 jumps, 3 spaces. You're gonna move 3 spaces. Which direction? That way. All right, so if you have 3.4, make 3 waves, right? 1, 2, 3, and then fill in the void. That makes this 3,400 millimeters is this figure, right? All right, then we'll do this one. Green here, 104 centimeters. If you start on centimeters, you're here. Right, and you were going to go to meters, right? It's just 1 jump. So you're going to go 1 space. Which direction? The arrow's already telling you, that way. All right. So if you take 104 and put in the decimal that's there, for a whole number it would always be behind to the right here. And then just make 1 wave. 1 wave, fill in the void. So this is realistically 1,040 millimeters. All right. Now we have a fair basis for comparison. That's in millimeters, this is in millimeters, and that is in millimeters. You could just as well have converted them all to centimeters if you like. Right? Doesn't matter. Right? So, what's the smallest one? Right. Evidently the original here in the middle. Right? So, let's see. Oh, you know what? There's a typo. Change this, make it, if I left it the way it is, then it would be this. 342 millimeters would be the smallest. All right? I actually invented a problem. It was a 3421. All right, but we'll stick with this. That's the smallest, right? Because it's the smallest number in millimeters. And then the next one would be this. 1040 millimeters. And then the last one would be 3,400 millimeters. You could, if you want to, do a couple of things. Right? You could put them in what they originally were. I'll just put this in a parentheses here, 104 centimeters. Right. And 3.4 meters here. Right. And then separate them by commas. We can do what I feel personally, and I'm not going to corrupt your opinion, but I feel is more elegant, right? Which is to incorporate a math symbol, all right? If this is smallest to largest, you could use a less than symbol like that, and it means the same thing. This is less than that, while this is less than that, right? Use commas or use a less than symbol if it's smallest to largest. Right? It would work just as well. Okay. All right, let's get into section 7.2. about usages. This is technically section 7.2 now. Some usages. Large units, sort of medium, and small units. Okay. Basically, the prefixes would kind of indicate. Alright, so when you see something like kilo, that's pretty much the largest, right? Unless you're going beyond the scope of the graph, like, you know, mega and giga, things like that. But and on the opposite side would be milli, you know? Right, whereas the base units are generally in the middle, right? There is some flexibility here, so it's more like a vague sort of rainbow, a spectrum of one color bleeding into the other. All right. Think of this as a spectrum. Okay. It's a little less defined somehow in the middle. Pretty much for sure. If you were talking about something that is a vast distance, right, which would be you would need a large unit. Right, so the appropriate unit would be something like the kilometer. You know. If you're talking about something that is fairly heavy, like even a person's weight. I should say a person's mass would be more appropriate. All right, then you would use a kilogram. Right? Let's see, on the tiny side, again, if you're talking about something like a tiny, very precise measurement, length measurement or width, like maybe the size of a coin, right? Then you're going to want to use something like millimeters. When you have more increments, you have the ability to make a more precise measurement, right? Tiny or closer together increments, right? If you had something like, again, a vitamin, right? The size of a vitamin, right? You would measure that in milligrams, right? Barney! I love Flintstone vitamins. I haven't had one in years, but I want one. All right. It's not like the Corona took them, right? Lysol, hard to get. Flintstones, you can still get those. All right. Anyhow, milligrams would be appropriate, right? If you've ever had some kind of medicine like amoxicillin, which is just dreadful stuff, all right. A lot of times it's like 1,000 milligrams, like that size. All right. Horse pills. All right. That's for the stuff in the middle here. Let's see. If you wanted to measure something like a person's height, right, you'd probably just go with a standard meter, right? A meter, again, is like a yard, right? A very tall person would be 2 meters tall, right? Because a meter is like 39 inches, right? So if a yard is 36, and that's 3 feet, and then 2 yards is like, 6 feet, all right? You'd have to figure it's larger than 6. Nonetheless, a meter, it'd probably be a decimal, like, 1.7 or something like that, all right? But you would go with a meter. If you're talking about something like capacity of a fluid, of a juice, all right, or a soda, right, then you're going to go with a liter. Right. A liter is like, I'm going to say a little bit more or less than a half gallon. Right? All right. This is kind of an interesting problem. If you had to calculate, right, square meters is converted basically to square centimeters. There's going to be sort of an amplification, for lack of a better phrase. First of all, let me start with this. Something that is a square meter, whenever you see this phrase, square, be suspicious. All right? This implies in a very vague way that we're talking about an area. Right? And an area, right, is something that is two-dimensional. So if it's two-dimensional, there's going to be a multiplication effect, really would be the best way to say it. Right? Let me start with, this is not to scale, but let's just say that this small little scale square that you see here, this is a square, I really swear. That's a square, I swear. All right. And then you have a much larger thing, which again, this is not to scale. Which is also a square. Right? Whenever you've had to calculate an area, there's a formula that has been quoted to you, right? Specifically for squares or rectangles. Trying to make that sort of subscripts. A rectangle. They will say length times width. In the case of a square, they could modify it even further. They could just say, well, there's no point in distinguishing one from the other because they're the same exactly. That's the definition of a square, right? All the sides are equal. I didn't draw it nicely, but all of the sides would be equal to one another. So what they do a lot of times is they just go, oh, well, it's a side times a side. All right? And then there's an abbreviation for that, which is to call it side exponent 2. Right? Whichever you prefer, this is probably the more intuitive way of thinking of an area, length times the width. You would need to take into consideration the dimensions this way and this way. And so if you went with the smaller one, for example, let's say that this was 1 centimeter square, like so. If you plug that into the area formula, right, the dimension this way, L, and the dimension this way, W, would just be 1 centimeter times 1 centimeter, which abbreviated again would be 1 times 1 is 1, but the unit would be centimeter squared, right? That little exponent of 2 is the abbreviation for this times this. Similarly, right, if this was 1 meter, right, and it was a square, it would have to be 1 meter this way. You'd go through the exact same calculation and say, all right, well, the area is equal to length times width, and then it's just 1 meter times 1 meter, which abbreviated would be an area of 1 meter square, little exponent of 2. The question is, let's say that we converted this into so many centimeters, right? What we would need to do, right, is figure out, well, in the one-dimensional measurement, and each one of these sides is just one dimension. This is 1D, right? Independently, and this is also one-dimensional. And then together they make a two-dimensional shape. right? What's the equivalent? A meter is how many centimeters? We would need to figure that out first. So here, borrowing the technique from before, is our number line. Meter, decimeter, centimeter, millimeter. And I really don't need the other ones, DAM, HM, and KM, but they would be over here. Right? If I want to convert this to so many centimeters, right, both of these, for the sake of a calculation here, right, I need to do the dimensions independently, one another. So you start here and you're going here. 1, 2. So it's 2 spaces. Which way? That way. All right. If I take 1 and I put a decimal there, then I'll make 2 waves. 1, 2. Fill in some zeros. 1 meter is 100 centimeters. Right? Remember, when you go down the list, you're multiplying by some power of 10. Which power of 10? The second power of 10. All right, 10 squared. All right, and that's the effect. In other words, 10 times 10. This is the effect. Scoot this over twice. When you multiply, it gets bigger. All right. That means that this dimension here would have to be the same thing, 100 centimeters. Now, if I put those dimensions into calculation, in place of 1 meter, the equivalent of 100 centimeters, and 100 centimeters, what's 100 times 100? All right. Well, the shortcut is this. Count the zeros. 1, 2, 1, 2. 1, 2, 1, 2. 1 times 1 is 1. If you want to be kind of traditional, there will be a comma here, right? The 10,000 is what it is. Centimeters squared. That's how much larger, right, a number you would get, right, if you expressed the exact same size. This is not proportionate, right? It's my bad drawing. All right, using the smaller units, you'd have 10,000 square centimeters. It sounds more impressive, right, when you hear it. All right, that sounds like somebody in business in marketing would be like, yes, here's a bigger number, but you're talking about the same thing. All right, 10,000 centimeters squared is 1 meter squared. Let me give you another little overview here, and then we'll do some calculations. In fact, I might just put it on the far side of the board here. We're going to have some measurements. This is funny because the geometry chapter really comes later, but we're going to be practical. Do this over here, sorry. It's still going to be practical to have some basic information. Measurements. If we are talking about measurements firstly in 1 dimension, right, then we are talking about a length. Right? Right. Some alternatives to that phrase are width, right, and height and side, right? But they still are, these are lengths just to distinguish one from another, okay? If we expanded the universe, right, to not just be 1 dimension, but 2-dimensional, right, then the subject becomes area, which I kind of alluded to already. All right, and in that case, there's 2 formulas that might be practical for us to know. There's the one we just used, which is this one, length times width. And then there's this one, area is equal to pi times the radius squared, right? Or the alternative to that, which is really the same thing, pi times the diameter divided by 2 first squared. Right. Just beware, these have different purposes. This formula for area is for squares, you can get away with using it, or rectangles. This formula for area is specifically for circles. Notice the pi symbol, right? What is pi? Because you have to do a calculation, right? A couple of things. Your calculator that is the type that we kind of expect you to have for this class, there's a pi button on it. So you can get a high degree of precision when you're doing your calculations simply by pressing this. Sorry for the reflection. See if I can get that without it. If you hit that, it will just tell you what pi is, at least to the edge of the screen. 3.14159, whatever it is, right? Remember, pi is an irrational number, which is code for, not to be secret, it's code for a very, very long number that is infinite, right? And that's non-terminating is the technical phrase, and non-repeating, which means it has no obvious pattern to it. So if you're going to employ an infinite number, right, you would, in theory, do the calculation for the rest of your life, right? And even then you wouldn't finish. So you can use, if you want, right, the approximate for pi, which is 3.14, right, in place of it, right? Just make sure that you follow the order of operations when you do your calculations, right? So for example, if you're just sticking with one side of this equation, then you have an expression. Remember, equations are made from expressions. So you just want to do the squaring first, and then the regular multiplication. If you happen to have a diameter, which is what this R and this D stands for, it's a circle. Right. The distance across the circle through the center is not a bit nicely drawn, but this is a diameter, often abbreviated D. And then a chunk of that, half exactly, would be a radius. If you're given a radius, just go ahead with this formula. If you're given a diameter, divide by 2 first. Right? That's why I put it in parentheses. Right. If we, again, expand upon the universe, and we go to the 3rd dimension, yeah. All right. Can't wait to get there. What? Washington, D.C. Washington, D.C. The president's calling. Yeah, what does he want? He wants you to stop teaching. Okay. Not gonna happen. Anyhow. When you're talking 3rd dimension, what becomes important is the subject of volume. Okay? So, and the formulas that would be useful would be these. I'll put them in black just not to conflict with the green that's here. There's volume of a box, essentially. The technical phrase would be rectangular solid. All right, but remember, if you're just going from one extra dimension to another, or from one dimension to another by adding dimensions, I should say, then the area formula basically expands. It would still be length times width, but then it would be the extra dimension of height, h. Right, for a box. Something, what is a box? But it's a, you know, it's a 3-dimensional real square. You know, squares, right, are mathematically flat. They're an abstract idea. They're not real. Right? They're an idea. I know that we refer to things like this piece of paper as being a square, but it has a thickness technically. It's a real object. Right. This book has a problem that involves the volume of a cylinder. so I'll give you that. It's an area. A cylinder is something that looks like this, basically. And it has two dimensions that are relevant. There's a radius in here, and then there's a height. Right? It's kind of like a stack of pancakes, if you will. If you found the area of the bottom pancake and then just kept adding layers of pancakes, you would build up a height. So this formula would be like so. Put this in blue. The area formula for a circle, pi r squared, and then times the added dimension, let's just call it h. Right? Lowercase h doesn't matter if it's capital or not. All right, so you hear the word volume, or have a picture of a box or a cylinder, probably can use one of these two formulas. If you're talking about an area, or there's a picture, all right, you probably use one of these two formulas. I would be remiss if I didn't try to teach good etiquette, right, insofar as math is concerned. All right, there's the ordinary way that we speak, and I'm guilty of not doing this. And then there's the technical way, right? And the technical way is precise. So in math world, it's a good habit to be precise. When you use a word like space, right? Even though I've heard people say, what is the area? It's the space inside the rectangle. Everybody knows what you mean when you say that, but don't say that, right? Reserve the word space for things that are three-dimensional, a volume specifically, right? When you mean basically the same thing, the inside of something, right? But you're talking about something that is mathematically flat, right? It has no thickness. It's just an abstract idea. Use this word. Use surface. Right? Can a three-dimensional object have a surface area? Yeah, but it's purposely ignoring the other dimensions. Right? If you're talking about an area that is the surface inside something, then it's 2D, use this phrase, area. When you're talking about the inside of something that's three-dimensional, and I would illustrate it by way of a box. All right, use this phrase. All right, out of space. If I in front of you. One other thing I could throw in here, let's see. There's two different perspectives of these measurements. From the perspective of radius, right, you could say, and this is totally true, a radius is half diameter. That's talking about something from the perspective of radius. Right? From the perspective of diameter, a diameter is equal to 2 radii. Okay. All right. That's a good overview basically for this stuff. All right, let's do some calculations. All right, I'll erase some of this. I'll erase this. Suppose that you had defined the area of a circle. It may not verbally, explicitly say that, but if you get a picture like this, right, and you have some dimension thrown at you here, it's a good bet that you are going to do that. First of all, there's a circle, which is what this is, and then there's a sphere, right, which is a ball, basically. Okay, and that's a very badly drawn sphere. It's kind of mutating one way, I'm sorry. This is a sphere, all right? You're not really responsible for this, but do distinguish them. A sphere is three-dimensional. a circle is an abstract idea. It's not real, right? It's mathematically flat, which means there's no third dimension. Right? It's two-dimensional. Right? It's flat. Right? And this is thick with two C's, right? That seemed worse. Alright, I'm gonna quit while I'm behind. Anyhow, when you are figuring out the area of a circle, and I didn't complete this thought, but I'm gonna throw a number in here, 76, and then I'll put it in centimeters. Alright. You have to decide, first of all, if you know that you're doing an area, right? Which of these area formulas you're gonna be looking at, right? If you're talking about a circle, it's this one, right? In either form. If you're given a diameter and when it's through the center across all the way, right, that's a diameter. You probably are going to want to use this incarnation of the area of a circle formula. Right? It's not wrong if you use this one, but you may have to do some of it in your head, the adjusting. Right. So let me get rid of this. The area is pi times the diameter divided by 2 squared, right? You recognize that 76 is the diameter, put a 76 in here, do include the unit, right? Right? And because this is in parentheses and you're obligated to follow the order of operations, why? Because we're just sticking with one side here. You really must do the contents of the parentheses first, right? You could, if you have a nice calculator, and you notice that this calculator has, parentheses buttons, you could, if you're very careful, right, make the adjusting, you just enter it in the correct order with the correct symbols involved, and it will probably work. I'll try, My instinct is just to go, all right, let me just reduce this to half first. What's half of 76? 3, 8, right? So this is really basically 3.14 times 38 centimeters squared, right? Which would you have to do first? The squaring, right? Because now you've reduced the contents of parentheses to just one number, right? What's 38 times 38? I'm painfully gonna do it. 64, 24 plus 6 is 30. 24 plus 2, 10. 9 plus 2 is 11. 1,444 centimeters, and because it is, this exponent doesn't just affect the digits, it affects the unit as well. It would be centimeters squared at this point. Right? And then you would have to do pi times that. If you use 3.14, you'll get a sufficient answer. If you use the pi button, you'll get an answer with a higher degree of precision. Let's say that you use the pi button. Because you get a better answer in theory. Here's pi, all right, 3.14, sorry, it's kind of blurry. All right, times the number that I have here, 1444, okay? You would have this, all right? 4,536.4 roughly. Kind of arbitrary the way that was rounded, but so be it. Right, we're not getting into significant digits here. Right. And that's that. Sorry, I'm boring myself. Okay. Right. Let's talk about volume now. Behind because we may need to get into that immediately after. the subject of volume, there's some alternative units that we have. Remember, volume is capacity by another name. If we're talking about the volume of something that is a solid or a gas, there is a preference for a certain type of units in sciences. Interesting. Versus when we're talking about the volume of a liquid. Right, you may have noticed this when you go shopping. If you've ever read cereal boxes, they have a weird unit, right? FLOZ. A lot of times on the Raisin brand it says 28 fluid ounces or something like that. That's what it stands for. Fluid ounces is just indicating, and that's FL, abbreviation for fluid, and OZ, which is where the Wizard of Oz comes from, actually. Ounces are from, I want to say, Roman times as well. Fluid ounces is implying that, I should just throw that out the window, is implying that you're talking about a volume, whereas regular ounces is talking about weight, basically. All right? So the only way to distinguish one from the other is by this extra abbreviation. Anyhow, we don't have to worry about the customary system, we have the metric system. All right? So, the preference for units when you're talking about solids or gases, all right, would be the cubic meter, or probably more accurately, some derivative of that, like cubic centimeters. All right. Gases, a lot of times, I mean, how often do any of those transport helium? All right. The tanks are probably in cubic meters or such and such. All right. But realistically, cubic centimeters is more common, right? When we're talking about liquids, on the other hand, liters, right? Milliliters is more common, milli. Yeah. Notice that in the case of centimeters and cubic centimeters, there's an exponent of 3. Whereas in the case of liters and milliliters, there would technically be an exponent of 1. It's not necessary. How come? Right? The truth is, as I was trying to mention before, right, this is expressing a volume using 3 dimensions of length. Right? So we've derived volume from length, another type of physical quantity. This is just saying that volume is a thing unto itself. Right? Which then brings us to the point of, well, what does one equal in terms of the other? In other words, 1 cubic centimeter equals how many milliliters? And the good news is this: they are interchangeable. 1 is to 1. In fact, there's an alternative here that I'm going to throw in as well. Right, I'll put it over here just not to mess it up too much. If you've ever seen on those doctor shows, like, there's always like emergency situation, and you see the nursing people and the medical practitioners going, I need 12 cc stat. CCs, I'm spitting, by the way, I'm sorry. Yeah. CC, I don't know why I'm slapping my hand, but I'm getting ready for my drugs, Anyhow, the CCs, all right, is an abbreviation for cubic centimeters. Right. Well, if you have 1 cc, right, then you naturally have 1 centimeter cubed. It's just a different way of referring to it, right? And that we've already established is 1 milliliter. Right, so it's very easy to convert from one to the other. All right, save this. This is very useful. All right. I don't know. Interestingly, the book actually mentioned this, so I'm just going to throw it in here as well. I don't think this is as common, right? But it bothered to mention it. 1 liter is 1 cubic decimeter, which means that it is 1,000 cubic centimeters. Right. Yeah, to me, the more practical units here are the liter and the cubic centimeters. Right. Because again, what that means, if you want to expand upon it here, if 1 liter is 1,000 cubic centimeters, then that means that 1 liter is 1,000 milliliters, right? Because it's a 1-to-1 ratio. Okay. But we could have figured that out anyway. How do we know? Because if we want to convert from liters to milliliters, that's naturally true. So going down the chart, or making moving to the right 3 spaces. All right. Let's do a quick word problem if we can. Let's just say that a nurse gives 3 cc's of a drug mixed into 100 cc's of saline solution, an IV basically, or some kind of a drip. Yeah. She has a drug, she mixes it, I'm gonna say she, but my mother was a nurse actually, so that was my instinct. 3 cc's mixed into a fluid, right, of 100 cc's, right. There's a couple of things you can tell right off the bat here. First of all, how many milliliters is that? And what is the total? Volume. And by total volume, I mean the drug plus the saline. Sounds like Visine. Did I spell saline correctly? I think I did. Alright, well, if this is in fact the ratio, 1 cc is 1 milliliter, alright? And if they tell you that it's 3 cc's without overcomplicating it, you can tell right off the bat that this has to be 3 milliliters. Right. They ask you for the total volume, alright? Question mark. Let's see, in milliliters, right. Or the other one, cc's, right? In cc's or milliliters, right? What would it be? Well, the drug is already established as being 3 cc, and the fluid is 100 cc, so they would naturally be 103 cc's, right? What is that automatically in milliliters? 103 milliliters. Let's do a cylinder. And I'm going to bring up that unit conversion business. Okay. Suppose we had a cylinder like this. Good. Soup. Okay. And you have very vague information, but you see a dimension incremented this way, and then a second dimension incremented this way. If this is a radius of 50 centimeters, all right? No, I'll just write the number. And this is a dimension this way of 148 centimeters. And this is a cylinder, a right circular cylinder if you want to be very technical. You have all of the information in this to just plug it into the formula and then answer any questions. Now, let's say hypothetically, you know, that the person who authored this a problem is a little bit particular, and they say, what is the capacity in liters? Right. I really should spell it the world way, which is R before E, right? But I'm an American, I can't help myself, stubborn, right? I should convert, right? So, here's our formula for the volume. And the reason that I would know to use volume is, first of all, a cylinder is a 3D object, right? It's real, even though this is a drawing to imitate that. And then we use this phrase capacity, right? So both of these things are referring to a volume, even if they didn't specify that, right? They're also talking about the unit for volume, liters. Let's just work with what we have, right? We should be able to recognize that if this is in fact a cylinder, that this dimension is an R, and that this dimension is an H. This is a radius, this is a height, right? And they would be appropriately fitted into the formula here and here. All right. If I just sort of superimpose those things, I always use little parentheses like this, sort of a pocket, a void that you fill in the number. I would put 50 centimeters in here, I would include the unit, and then 148 centimeters in here. And then just calculate what the volume is first, right? There's no sin in converting everything to liters first, right? But that's what they gave me to work with, so my instinct is to do that, right? We could just use 3.14 or some other derivative of pi, if you like, right? Follow the order of operations, right? You have the choices between regular multiplication here and here, and amped up multiplication, which is squaring, right? You should square first, right? Which means realistically, this is 3.14, whatever it is, right? Times 5 times 5 is 25 with 2 zeros, is 2,500. And then you have centimeters squared, right? And then 148 centimeters. When you have centimeters squared times centimeters technically to the first, you add the exponents. So that's why the answer will ultimately be centimeters cubed, okay? All right, I'm gonna enter this into the calculator. This is just multiplication at this point. Okay. So let's see. Here, I'm gonna go with very fine, precise pi here. Pi times 2,500 times 148. And you get this enormous number, right? It's hard to see, sorry for the glare. Does that help? Barely. 1165389.5. All right. So that looks like 1 million and change. Right. I'm going to write it out. The volume calculated here, all right, using centimeters as the dimension units, right, is this figure, right? In the sort of historic way of writing it with commas. 1,162,389, and because nobody decided to round anything, right, I'll just terminate it here, right? Centimeters cubed, right? That's correct, right, in that type of unit, right? But the question is in liters, all right? So here's where I want to sort of segue into that old conversation from way back. I mean, I kind of just broached upon the subject a while ago. Here's this. I'm kind of proud of this, right? This thing in the box here is a model that I feel is good for life, right? I'm not giving you the mulch, I swear, all right? I'm trying to encapsulate this, all right? Think of things when you're trying to do unit conversion, all right, as being whatever is given to you times some kind of a fraction, which is called a conversion factor. And incidentally, the conversion factor, you could at will flip, you know, to whatever orientation you like, right? Whatever is practical. You do that calculation, it will spit out what you want. This is more or less like a little machine, right? What I have here is, you know, the rare instance of having to do multiple conversions, right? It's kind of fun. Like, if you've ever taken a chemistry class and they throw in this phrase around stoichiometry, right? Which ends up being a lot of unit conversion.
That's really the way that would be practical to think about it, right? Like this little machine where you have to sort of rig up all the parts, right, strategically, all right, and then it will systematically eliminate the units for you. All right, let me walk you through it. All right, this is again overkill. If you intuitively know how to get to the answer, it's cool. All right, I don't want to dissuade you either. But look at this figure that we have to work with. All right. 1,162,389 cubic centimeters. All right. Erase this just because I don't need it anymore. All right. And I'm going to set up something. I'm going to put this out of the way, right? Just for reference up here. Right. 1,162,389 centimeters cubed. Okay. If I want to do a unit conversion in more or less the chemist's perspective of doing it, it's practical. All right. I'm going to take this model that I have. And this model says, all right, whatever is given to you, right, if you are very careful, you can multiply this by something that looks like a fraction. Right? It's a conversion factor. Right? That you could rearrange the parts at will, up and down. Right? And that will spit out what you want. Okay, well, what am I given? All right, let's examine the units. Not really given, I calculated this, but for all intents and purposes, I'm given a certain number of cubic centimeters. Right? This enormous number here. 1,162,389. All right, and I'm going to multiply by something in a moment, but I want it to spit out regular, ordinary liters. Liters. All right, so I'm just going to use L. What I would have to do, if this is what I'm given or what I have, right, and this is what I want, right, I would have to ideally select a conversion factor that involves the two of these things and have it arranged, one thing sitting on top of the other, in the peculiar way that causes an elimination effect, a cancellation effect. So here's what I'll do. I'm going to put a little bar here like a fraction. Right? I'm going to say to myself, well, I'd like cubic centimeters to get lost. Right? All right? So in order to accomplish that, if this was one fraction sitting next to another fraction, right, then I would need to put cubic centimeters down here, right? Whatever it is. Right? We'll fill in the numbers in a minute. Right? And then I would need to be able to convert cubic centimeters into some of the unit that gets me a little bit closer. Now in this case, the best that I have is that I can convert a cubic centimeter to a milliliter, right? Whatever it is, right? What's going to happen is that I'm going to basically need another conversion factor. It's never going to be this extreme really, but I'm going to put another little parentheses with another little fraction-esque looking thing adjacent. All right, I'm going to sweep that in here. All right. So this will be a second thing that I would have to multiply by. All right. A second conversion factor, and that's going to spit out, again, the thing that I really want, which is so many liters. Again, don't pay attention to the numbers yet. Just pay attention to the units. Right? You got cubic centimeters here. So if I want it to go away, I have to put it in a denominator here. Ultimately, I want milliliters to go away as well. Right? I just needed a sort of the bridge from here to there. All right? So I'm going to put milliliters down here as well. And then the thing that I could easily convert to. Milliliters and liters is very easy to convert to, right? Because they're the same type of thing. They're for the same purpose, inherently. All right? Whatever the number is, whatever the number is. All right? Now that this machine is basically rigged, just kind of narrow your focus from here to here for the moment. All right? What I can do is start to put the numbers in the appropriate places. I always do that as an afterthought because the unit cancellation is really the beauty of this. All right? And you cause things to cancel by putting them diagonal to each other, right? It's kind of like this. If you had 2/3 times 1/2, right? Yeah, you could do 1 times 2 and get 2, and then 3 times 2 and get 6, and then divide by 2 and get 1/3, right? Or you could strategically cancel out the similar factors that are one above and one below. They're diagonal, essentially, right? That's doing the simplifying first, right? That works with numbers, but it also works with words, and it also works for abbreviations for words. This is a beautiful thing. All right, so let me put in the numbers now. All right. The relationship of milliliter cubic centimeter is 1 to 1. So if I wanted to, instead of writing it out sort of horizontally this way, I could write it in a fraction-esque sort of way, conversion factor. It would be putting it as a 1 sitting on top of a 1. Right? Only purpose here is just the elimination effect, the cancellation effect. When we get to the next one, what exactly is the relationship between milliliters and liters, right? In 1 liter, there are 1,000 milliliters. Right? So here's what's going to happen now. All right? I may have to end up writing this backwards. We get the satisfaction having rigged the machine to cancel stuff, right? If this is sitting here in given, and I strategically rigged it so that it cancels here, so be it. This particular problem required a second conversion factor. So again, I rigged it so that this would happen. This is all by design. Right? What does that leave me with? It leaves me with a bunch of stuff that is numbers basically on top, and the unit that I want. All right. So it would be 1,162,389 times 1, which is not changing anything, right? And then times 1 again, which means that the number on the very top is going to still be this sucky number, but it will now be in liters, right? And then below the line would be 1 times 1 is 1, and then this 1,000 would be the bottom here. All right. And all of the units again have canceled except the one that I strategically want. This is a little tedious at first because maybe you've never seen it done before, but I'm telling you, once you get used to it, you go, ah, this is fantastic. I don't know why they don't teach me it this way outside the chemistry world, but it is like, that's the way it ought to be taught, all right? To strategically rig something to your advantage. All right, anyhow, the bottom line is you got this disgusting number here divided by 1,000. So divide these two things. The effect, without even using your calculator, is going to be what? When you divide by 1,000, you are dividing by some power of 10. And the effect, all right, the effect of dividing by a power of 10, whatever it is that it moves the decimal place which way? All right? This way. The number of zeros in this case, or whatever the power would be, 3 in this case. 1, 2, 3. What does that mean? It means that this volume, expressed in the larger unit of liters, is really 1,162.389, whatever it is. And you could ditch those if you like, liters. Right, you might round it if you want, but that's whatever. Right? The bottom line is that it's 1,000 and change, right, versus 1,000,000 and change. Why? Because that's a big unit, and that's a puny little unit. And they're still talking about the same thing, volume, this weirdo cylinder. All right? It's supposed to be, because I took it from the textbook, a hot water heater. Right? So boiling water. All right? Well, whatever. That's just, all right, let's get into mass and weight and temperature. We're on time, that's what we do. Okay. If you have an intuition about something, right, that's a blessing, and I would never want to talk you out of it. The only point of this newfangled stuff that I've mentioned is that it's the back door, you know, and maybe it's the path of least resistance in the long run. So be open to the possibility. Kind of save it in the back of your head, even if you feel sketchy about it, like, maybe I could do something this way. Okay. So here we go. Here's 7-3 technically. Make it up for lost time. We're going to talk about mass and weight and how they are different. We kind of use these things synonymously. Yes, you can kind of get away with it, but they're not the same thing. They're different physical measurements. Right? If you were in a physics class, that's really where this would become obvious. Right? And I will pay homage to my former overlords, the physicists. Right now, wherever they are. Right? A weight is a force. Right. From the perspective of a physicist, right? A mass is a fundamental physical quantity. Right. The fundamental measure of matter, of material, if you will. Right. One could calculate a weight, right? Using a mass, right? There's a formula, right? Famously, this you're not responsible for it, but this is Newton's formula, right? Mass times acceleration, right? If you just replace acceleration with gravitational acceleration, then you would just change this to weight instead, right? It's basically two numbers multiplied together that make a weight, right? And one of those things is indeed a mass, right? Right? A fundamental measure of material. Right? Anyhow, to make it a little bit more clear, right? Think about it this way. Right? A weight changes, right? Weight depends on where you are. Right? This depends on location. Right? It will fluctuate, that measurement. Why does Washington, D.C. want me so much? Yeah. I'm just curious. Hello? In regard to what? Yes. It has actually, not to cut you off, I have, it was resolved. It took a while, but I went through other avenues. August, I want to say. Okay. All right. All right. I appreciate it. Thank you. Take care. You too. I wasn't expecting a call from my congressman. All right. I don't know if I had told you this a while ago, but I was had issues with government agency. So if you ever have an issue with a government agency, right, contact your congressman. I don't like things to get to that, but sometimes they're sort of like your godfather, you know, in an ideal world. So you can use them. Anyhow, I'm sorry to distract from this, but they called me 3 times and it said Washington, D.C. So I'm like, I thought that was a scam. Right? No, apparently it was my congressman calling me. Alright. Anyway. Weight depends on location. Right. And let's see, what else? Person. Okay. This does not depend on location. Right? famously, if you were to travel to the moon, right? How many of us will ever have that privilege, right? Of the experience, right? Your mass here and there would be identical, right? But maybe off a little bit because you had a sandwich en route. some astronaut ice cream, all right? And now you have more mass, right? Or you went to the bathroom, But by and large, you have the same mass in two places, right? This is forever, unless you do some exercise or you eat something, all right? We'll go to the bathroom. Your weight, however, would be different. Right? That's the classic example you always get quoted to, right? The moon, right, has 1/6 a gravitational pull as the Earth. Right? Right, so that basically means that if you measured your weight on the moon, you would mysteriously seem to have lost weight. Right. Whatever your weight is, divide by 6, and that's basically what you can expect your weight to be on the moon. Nonetheless, your mass will be the same. Right? And the unit that we prefer to measure mass in is the kilogram. Right? Versus the customary system is pounds. Right? Again, it's from Latin. Right? It comes from the Romans. It's that old. Right? The unit, right? Which again we've gotten only by way of the British Empire. Right? If you wanted to, you could certainly Google search this, but this is a fun sort of factoid. 1 kilogram is equal to 2.2 pounds. Now I know I just got through the conversation saying they're not the same thing, so how can you relate one to the other? Because they're proportional, right? Not the same, but proportional. That's why a conversion factor exists for these. 1 kilogram is approximately, I should put a little squiggle equals here, 2.2 pounds, LBS. LB. Okay. There is the book also mentions this. There's a ton, of course, right? We're all familiar with a ton, right? 1 ton in the United States is 2,000 pounds, right? But that's not to be confused with 1 metric ton, which I want to say is spelled that way, which is probably the original way, and therefore I guess the correct way. Right, 1 metric ton is 1,000 kilograms, right? And it's abbreviated like a lowercase t. Okay. Anyhow, you can convert one into the other, the U.S. ton to a metric ton, but it's probably not going to happen. All right. More likely, you would do something like this: how many kilograms is how many pounds? Right. So I just got through the conversation of conversion factors, right? What is a conversion factor? This is a conversion factor, something that relates one unit into another unit, right? It's just disguised, right, as a fraction-esque looking thing, right? Meaning that there's this line here, right? If it's practical to you, all right, orient it so that kilograms is on top, all right? If it's practical the other way, you have totally the freedom to switch it like so. Right? Whatever way would be to your benefit. If it helps you to cancel out kilograms, put kilograms on the bottom. If it helps you to cancel out pounds, then put pounds on the bottom. Just make sure that the appropriate digits are attached to the appropriate unit abbreviation. Okay? Right. Even more practical than this. Let me get rid of some of the stuff here for a moment. Because the volume of a liter of water is defined, right? 1 liter of water is defined as 1 kilogram at standard atmospheric pressure and temperature, which I want to say is probably 20 degrees in 1 atmosphere. Don't quote me on that, but at standard atmosphere and pressure, temperature, this relationship is true. These relationships. Okay, this 1,000 cubic centimeters is equal to 1,000 milliliters, right? Come on, MathNet. All right. We already kind of knew that anyway because they already had a 1-to-1 relationship. Because we already know this, all right? And yes, that's cc's. All right. This is true. All right. It just so happens that there's one extra item here. Come on. 1,000 grams, right? Which is 1 kilogram. If it's 1,000 is to 1,000 is to 1,000, then it's 1 to 1 to 1, right? The only thing that you would have to adjust here is that this would be a fraction of a kilogram, so there'd be 0.001 kilograms technically. Right. Or you could say 1,000th. Okay. Anyhow, save this much information because this will be useful to you probably in the homework. Okay, green is kind of dying. And let me do some examples with you. Okay.
Wasn't sure if you were following.
I am technically now. Guess who called me? My congressman.
You mean our congressman?
Our congressman from. Yes.
So
I'm
selfish.
sorry. Oh. Oh.
Such an asshole.
We're on film. This is all coming to you live. All right. Anyhow, just go off these. Sorry. Very unprofessional, Ziegler. Meanwhile, I'm filming from my house. All right. Which I will do because this is what Corona World wants. So anyhow, moving on. Back to Math World, the most apolitical, asexual, sterile place on earth. Let's see, a Druid picture. All right. I digress way too much. Okay. Suppose that you had this lovely fish tank. Isn't that great? Glub glub. And I'll sort of simulate that with some really tempestuous sort of current in your fish tank. You have a worried looking fish here. All right, here we go. Glub glub. Looks like Nemo. Okay. This is, in case you're not sure, it's a fish tank. All right, I swear. And it has these dimensions. All right, let's say that in this dimension, it's 50 centimeters, favorite number of the textbook for whatever reason, and in this dimension, it's 1 meter, right? And then this dimension is 250 millimeters. Okay. If you're talking about something that is a fish tank, you are indeed dealing with something that's three-dimensional, namely something that is real. All objects that are real are three-dimensional. Yes, we live in 4 dimensions. The 4th dimension, though, is not a spatial dimension, it's time. Okay? So we have objects that the only way that we can really understand or grasp 4 dimensions is that we have our real objects that are, exhibiting movement somehow, right? And time transpires. Anyhow, look what the issue is right off the bat. Even if you were going to calculate the volume of this fish tank, and that would be the first thing, all right? In liters. We have this issue of basically them having different units. So this is in centimeters, this is in meters, and this is in millimeters, right? It's probably to our advantage to convert everything to maybe meters, because it's the larger unit. The only downside to that is that you're probably going to get a decimal, and decimals are not fun. I mean, yeah, you have a calculator, but if you're trying to rig up something to do it by hand as easily as possible, let's go with the medium one, right? You can make them all millimeters, you can make them all meters, you can make them all centimeters. But my instinct is, let's do the mid-size in between, right? So I'll convert each of these. Right? How do we do that? Well, we could employ, at this point, our little line here. We have meters, decimeters, centimeters, and millimeters. And yes, they're on the other side, but we're not going to need it in either case. Right. If you wanted to convert 1 meter, you start in here, to so many centimeters, 1, 2, then it's 2 spaces. So you take the number 1, and then you make a dot for the decimal point, and then make 2 waves, right, which means that this is now 100 centimeters. Right. Let's see. When you're going from millimeters to centimeters, you're going the other direction finally. So you're going to start here, and you're going up this way, right? Just 1 jump. So if you take the number 250, and there's your decimal point as it would start, and then you just scoot it up, you're heading this way now, right? 1 space. It's easier to just simply say that this is 25 centimeters, right? We're going to use basically these 3 numbers when we calculate our volume, right? It's going to be in centimeters though, not in liters. So we're going to have to do some kind of a unit conversion at one point. I don't really want to erase this, so I wonder if I could get away with sort of putting my little machine here. Right? Let's see. Let's start with calculating the volume now, since that's what's requested of us. If we take the volume, let's take into consideration what basic shape this is. Would you say that this is a cylinder, or would you say this is basically a box? It's a box filled with fish, all right? Rapid, dangerous, tempestuous, hurricane-driven winds, all right? Hurricane-forced water, all right? Poor fish, all right? He looks worried, see? He's got sonar or something. Right? The formula is length times width times height because it's 3-dimensional. Right? Remember, length and width and height are all the same type of a measurement. One-dimensional, one-dimensional, one-dimensional. All right? It's just using a different label, right, to specify this one, and this one. Which is which? It's arbitrary, right? My instinct, again, not to corrupt your opinion, is that, well, in the normal sort of orientation of our lives, this is more or less the height dimension, right? So let's just call this 50h, right? Let's call this the longest one, the length, right? And then let's call this width, right? If I insert those numbers, 25, 100, and 50, right? I would technically put them in this arrangement, right? 100 centimeters, right? In place of width, all right, I'll put 25. Right? I'm using little parentheses again because, again, I try to avoid, I'm trying to circumvent any sort of issue with squaring. It's not happening in this, but it's a good sort of rule of thumb. Right? Make little pockets that you fill. All right. Times, let me have this height here. All right, 50. Okay. Now, what happens with the units? They're all technically exponents of 1. I know nobody bothers to write that, but that's the logic behind this being so many centimeters cubed. It's the abbreviation for centimeters times centimeters times centimeters. 3 iterations, 3 clones, if you will. So put a little exponent of 3 here. And yes, you would read that as cubed, because it comes from that sort of a shape. Right? Now, as for the numbers, all right, you could do it in your head, right, or you could use a calculator, either way. I'm going to do it a little lazy now because I'm getting stupid. Getting very tired. All right. So you got 100 times 25 times 50. All right. So you have this enormous figure, right? 125,000. Right. So I'm going to put that here. 125,000 cubic centimeters. Right? So
we love you, like uncle included.
Yeah.
We all love you.
So, right. What I'm going to now need to do is I'm going to have to rig another one of these little conversion factor machines, if you will, so that it changes from the unit that is cubic centimeters into the one that we have. I'm sorry I keep sort of saying that, but I'm trying to convince myself. All right, so here's what I'll do. Here's my model. All right. What is given is basically what is calculated times, perhaps in this case, is there any more than one? I'm going to need 2. Conversion factors. Conversion factors, all right, will eventually spit out what we want. So that's basically a slight expansion. I just know from having done the problem already that it's going to take 2 conversion factors, at least the way I did it. All right, may not be necessary, but what's given? The thing that I just calculated is 125,000 cubic centimeters. So I'm going to basically fill this void with that number. All right, so you have 125, 000, and I'm going to include the unit because it's to my advantage. So cubic centimeters. All right. Because this is what I have to start with, and this is what I want, liters, all right, I'm going to strategically have to cancel out cubic centimeters. So I'm going to first put cubic centimeters here and see what I can get away from my tables of what I can convert to. All right. I can convert from cubic centimeters into milliliters in either the 1,000 to 1,000 ratio, which is exactly 1 to 1, or using these numbers instead would be more practical. Bottom line is that I can convert from cubic centimeters to milliliters in basically one step. All right? I'm going to leave out the numbers just yet. I'm trying to get you sort of in the habit, if you do this, all right, to just stare at the units, because that will kind of guarantee and guide you, all right, in the right direction. If I want to convert from milliliters now to liters, I would have to strategically write milliliters down here, diagonal, for the sake of cancellation eventually. And then I have liter up here. All right. So now I'll put in the numbers. All right. There's a 1 to 1 ratio of milliliters to centimeters. Yeah, I could have put 1,000 and 1,000 here, but it wouldn't accomplish anything. So I'm going to go with the same relationship using smaller figures. All right. 1 liter is 1,000 milliliters. Right. So now I have the pleasure of basically canceling out this stuff. All right. This is rigged to cancel this because they're diagonal. This is rigged to cancel this because it's diagonal. And the only unit that is left over is the one that I want. Right. Always have the thing you want on top on the very end. Okay. Now, it could be, if you wanted to pay attention to the digits, they're just ones, really. You would have 125,000, all right, times 1 is not changing it. now in the unit of liter, right? And on the bottom you have 1 times 1, right, times 1,000, which is just 1,000, and no unit because you already canceled it. Right. Then there's this shortcut, right? You could use your calculator certainly at this point, right? But if you divide something with zeros by something with zeros, right, this will always be true. It's dividing by common factor of some power of 10 without really consciously thinking of it, but you can cross out pairs of zeros. So if you got 3 here, you can get rid of 3 guaranteed, right? And then the leftovers have the same exact relationship. Bottom line is that the volume is 125 liters of water. Now, if there was a second question here of what's the volume and then what's the mass of that, and I'll put it here. What is the mass of the water? We could take advantage of these conversion factors. We have established that so many milliliters is equal to so many kilograms. Right? So if we have this many liters, this is another version of the given times the conversion factor equals what kind of problem. 125 liters times a certain conversion factor will inch us closer to what we need, or what we want, which is apparently, what is the mass? And the mass is in kilograms. All right, we can convert this to so many kilograms. All right. Another one of these little machines, but again, strategically rigged so that it cancels out liters and leaves us with kilograms. Use these more or less horizontally written conversion factors and write them more or less in the vertical, shall we say, fraction-esque style. All right. We can convert from a liter, right? So I'm going to cancel it to something that is congruous. All right, a milliliter. All right. We can convert a milliliter to a gram. All right. So I'm going to put this on the bottom. And I'll put that G there. And I would end up needing yet another one of these conversion factors. So I'll scoop in another one here. Okay. Kilogram, pardon me, if I want to cancel out grams, I'm going to put that down here, and then kg is up here. All right, now I'm going to put in the units. Let's see. In 1 liter, there are 1,000 milliliters. In 1 milliliter, there is 1 gram, apparently. They're not in one inside the other, but they're related, I should say. In 1 kilogram, there are 1,000 grams. Right? If I'm not to, you might be wondering, where are you getting this 1,000 from, buddy? Right, let me just remind you of something. I didn't draw it on this, but remember the sheet that you have from before. The number of spaces, basically, from gram up to kilogram, is 3 spaces. That's a power of 10, that's a power of 3, which is 1,000, right? If you went 2 spaces, it would be a power of 10, that is a 2, that's 100, all right? If you went up 1 space, it would be 10, which is a power of 1. It's a power of 10 to the first, I should say. Anyhow, this is good to go. It might be overkill, but it illustrates the point, all right? This is rigged to cancel liters, all right? This is also rigged to cancel milliliters, ultimately. And it's rigged to cancel grams. So, what do I have on the bottom here? Right, I can make that look like a fraction really easily. 1 times 1 times 1 times 1,000, which means the bottom of this is going to be something divided by 1,000. Right? And the tippy top, actually I can get away with doing something else as well. Right? If you notice, right, there's 1,000 above the line here, and simultaneously there's at 1,000 below the line here. So I can circumvent doing this at all. Right? This, even though it's all the way down to the end here, there's a number above the line and a number below the line is identical. Right? Even if they were not identical, but they had made it the same factor, you could cross cancel and simplify. All right. Yeah, I know that there's a lot of multiplication going on here. The beauty of this is that it's rigged to be multiplication, so you could do things in any order that you need to, and you can move the parts around, right? So that leaves you with a 1 behind and a 1 behind here. That's 120. The bottom line is this: 125 times 1 left over times 1 left over times 1 leaves you with exactly the same number. All right. 125 liters of water weighs 125 grams at standard atmosphere temperature and pressure. Standard temperature and pressure, no atmosphere. I want to say 20 degrees Celsius. Okay, so one more thing and then I'll stop, right, which is the temperature is another one. Battling matter. I like this very much. We have two temperature scales. Temperature. Temperature scales. Alright, which are good to know. Alright, one is metric and the other one is not. In the United States, the familiar, customary temperature scale is the older one. Right? Do you see a pattern here, America? Alright, again, I like old things, right? I used to collect comic books, as a matter of fact. All right, but when it comes to progress, social progress, and scientific progress, you can't be too rigid. You have to open your mind, right? So, the older temperature scale, not too much older by comparison, was the Fahrenheit scale. That's an always. Fahrenheit. There's a German guy living in Poland. All right. And then there's Celsius, which was a Swedish dude living in Sweden, like Swedes do. All right. Here's how close apart in time they were. All right, which should give you an idea of where sort of Western civilization at least was in terms of scientific thought. The 1700s, right? The Fahrenheit scale is from 1724. And interestingly, the Celsius scale is from 1742. They're the same digits, more or less. What do they call that? An anagram, if it was in letters. Anyhow, I just think that I found that charming. I'm like, oh, really? All right, this is the older one, and this is the one that we have stuck with here for as long as we have, for better or for worse. All right, Fahrenheit is named after this dude, isn't it? You're not responsible for this. Daniel Fahrenheit. All right, Daniel Gabriel Fahrenheit. David S. Pumpkins. All right. All right, and then Celsius is named after, he has a much cooler name. If you ever have a kid, right, here's a cool name, right? Anders Celsius. Right. As a kid who's going somewhere. All right. All right. Swede, German guy living in Poland. All right. Here, how are they different? Well, the Celsius scale, which is the metric one, purposes, the scientific scale accepted, all right, is based upon something a little bit more intuitive, perhaps. Right? It's more practical, certainly, for this reason. It's based upon the freezing and boiling point of water. Right? But taken one step further, all right? Figuring out how to increment them exactly 100 increments apart. Right? Okay. The Fahrenheit scale, on the other hand, is based on several things. Somebody had read, I don't know if this is true or not, just taken for granted from the internet. All right, it was based upon brine, all right, rather than water, right? Now, tap water even is not pure water. Man, fly, please, dude, bug off, all right? Gnat, like a cat with a ball, all right? Brine is like, pickle juice. Alright, so it's based upon several things. Right? Perhaps brine being one instance of this. Like he may have done the experiment, or he may have basically been adapting this for a while, and this was one thing. Alright, brine has water in it, certainly. Right? But interestingly, if you consider the freezing point of water on this scale, what's the freezing point of water on Fahrenheit scale, Americans? 32 degrees Fahrenheit. What's the boiling point? This is less, commonly known, but it's 212 degrees Fahrenheit. How far apart are these incremented? If you subtract 212 and 32, what would you get? Interestingly, 180 degrees. All right, where have you heard that number before? All right. As you guys know, from having looked at Babylonian math, right? It was a number system based upon what? 60, right? And that has a vague reference to our calendar, So like a less precise calendar, instead of being 365 days in a quarter, which is even not perfect, because it changes ever so slightly. 360, right, is divisible by 60. And 180 is exactly half of 360. So it seems like this was, I don't know for a fact, but I would guess, right, very strategically incremented in such a way so that that magic number was in between these two. All right. On the other hand, what's the boiling and freezing point of water on a Celsius scale? Something that, this is why I say it's probably more intuitive. Freezing is 0 degrees Celsius, right? Boiling is 100 degrees Celsius, right? It is arguably an easier system for that reason, not just an arbitrary, older, antique sort of number, if you will. It's not fair to call it antique, maybe, but you get the meaning. All right, it's a little bit older fashioned. All right. Anyhow, there's two formulas, all right, that are good to know. I'm going to put them above here, and I'll do two examples with you, and then I'll stop. Because I'm getting a little goofier than normal. If you are going to convert, all right, from Celsius into Fahrenheit, meaning that this is set solid for Fahrenheit, that's the F, then you would want to use this formula, C plus 32. If you want to convert from Fahrenheit into Celsius, and in that instance you would notice that this is set equal to C, only on one side. This is the inverse of that formula, and it would end up having this extra parentheses. So we would have to basically do subtraction first. And in this case you would have to do multiplication first, technically. Okay. Subtract first. In this case, you have to multiply first. Okay. All right, let's do an example. Oh, and let me just show you one thing else in the packet. All right. Again, we Americans have a hard time with converting to something that even the rest of the planet is doing. It's bandwagoning is what it is, right? Because of the feelings that we have. Now, who often, would think, geez, I have a feeling. Yeah, I hate math. That's the feeling, right? No, I mean, like even a number, right? If I quoted 20 degrees to you, right? You as an American would probably go, brr, But if I said 20 degrees to somebody who was maybe, South American, or from Africa, or from Asia, or Canadian, where they use the Celsius scale, all right? And that's just next door, 20 degrees is room temperature. It's a nice day, right? They don't go brr, Right? Anyhow, there is a nice table here, as you can use as a reference, right? What Celsius would be related to in terms of Fahrenheit, just to get your feet wet, right? Not too wet. All right. Mild spring day. All right. Let's do a calculation, and then I'll stop. All right. Let's say that we want to convert a 60 degree Celsius hot water heater, because this book loves hot water heaters. To the Fahrenheit scale, right? Maybe just to, be more sympathetic to our American compatriots here, right? We're going to convert this into Fahrenheit. So, this is what does that. How do you know? It's set solve the F, right? So I would insert a 60 right in here, right? And again, just sort of make it look like a little pocket and maybe disguise it as a fraction as well. We would be obligated, since we're just sticking with the right side of the equation, right, to follow the order of operations. So you could do brute force 9 times 60, figure out what it is, divide by 5, and then reduce that, and then add it, right? Or strategically, try to simplify. What I'm getting at is that if you looked at it like this, you could do it by hand. You don't need a machine, right? There's a relationship between 5 and 60 for sure, because the rules of divisibility of 5, even if we don't have our multiplication tables of 5, right? But this ends in a 5, this ends in a 0 or a 5, so they're both made of the number 5 somehow. 5 divided by 1, 5 divided by 5 is 1, right? 60 divided by 5 is 12. I know my multiplication tables of 9, right, and 12, and I know that if I multiply these two things, the bottoms are just 1, that this is 108. If I add 108 and 32, I get to the Fahrenheit temperature, right, which is equal to 140, 100 degrees Fahrenheit. Sorry, that's kind of faint. Right. Green's dying on me, baby. Okay. All right, next one. Let's say you wanted, this kind of tickled me, convert a 55-degree wine cellar. Because how many of us have one of those? I live in an apartment. I don't own a wine cellar, but that just tickles me. I made wine a lot, but I don't have a wine cellar. Imagine if you went downstairs just to yell. Have a wine cellar. Alright. Pun intended, right? Alright, so we're going to insert 55 in here. And because of the parentheses in the formula, we must subtract first. All right. If you subtracted 55 and 32, you get 3, you get 23. So that means that what's left over is the fraction 5/9 times 32, 23 over 1. Right, this is subtraction here. Unfortunately, there's no simplifying because the greatest common factor of these two things is just 1. So simplifying by that is not going to change anything. You're kind of stuck using brute force multiplication. All right, 23 times 5 is 15 is 115. So you have 115 divided by 9. All right, which again, if you do it brute force, maybe put some zeros in here. 9 goes into 11 roughly once with the difference of 2, short division. 9 goes into 25 twice, which is 18. The difference of 25 and 18 is 7. So 7, 0. 9 goes into 70 roughly 7 times, which is 63. And the difference is again 7, and this repeats. All right, which means that the Celsius temperature for 55 degrees Fahrenheit is, I'm going to round it since it repeats especially, is about 12.8 degrees Fahrenheit, something like that. Okay. Celsius rather, sorry. So Celsius. All right. That's it. Okay. So thank you for sticking with me for 2 hours, 2.5 hours. A good sport. All right. For homework, all right. You'll notice I updated the MyLabs. All right. I updated the due dates. All right. Updates. All right. Due dates. All right. So what it will coincide with is this. If you look at the full calendar that we have here. Right, today is the 14th of October. The next test in theory is on November 9th. So the assignments in between now and then, these we just discussed, and the remainder of 7 and those of chapter 8 will be due by the end of the day on this Monday. Right, so in my lab, one thing you'll notice is that the date is, due date is 11/9 it should be, or something like that. Right. If you notice that it's a little wacky, whoever programmed it, right, the software, I mean, they programmed it using Mountain Time rather than Eastern Standard Time, which is where we did, right? So it might say, 12:59 a.m. as opposed to 11:59 p.m., all right? Because of the difference in an hour according to those scales. They're the same time, that's just weirdly referring to Central Time. All right, anyhow, so what you want to do, right, work on these just to keep up to pace, all right, and then I'll see you again on Monday, all right, we'll do 7.3 and 7.4, all right, thank you folks, all right, sorry about the phone call and among other things, all right, be careful out there.